All right. Today we're going to be looking at a satellite that's in orbit around a planet. It's orbiting at a distance of 9,000 kilometers from the planet's center, and it's orbiting every 45 minutes, so it is really booking it around there. And we're given the satellite's mass, and we're wondering how much force it takes to keep it in orbit. Remember, if we've got our little satellite here, okay, clearly it's not drawn to scale because the satellite is almost the size of the planet. So anyway, we'll just enjoy that little fun fact. Remember that as the satellite is moving around, it would depart in a tangent path and just head straight on away if there were no force on it. But since there is a force, the force of gravity from the planet acting on it, that force of gravity actually holds it in a circular path around the planet. Okay, so here's our satellite, and the question is, how much force does that take in order to keep this satellite moving around, moving that quickly, that far from this particular planet? Okay, well, let's go about finding out. Remember, when it says how much force, what we're really asking for in this case is the centripetal force, the force that's pointing toward the center of the circle that's holding that object in a circular path. All right, and that's what we're going to be curious about. Let's see what else we know. We know that this is a distance um, in orbit around a planet at a distance of 9,000 kilometers from the planet's center. Good, because we actually will need to know the distance center to center. And so in this case, that's already given for us, and that is 9,000 kilometers. Now remember, that's not a standard unit. We need to convert to meters for our distances. And so that's going to be 9,000. And then put 3 more zeros on there for meters. And so then that's actually 9 million. Or I'm probably going to express that as 9 times 10 to the 1, 2, 3, 4, 5, 6. 9 times 10 to the 6th meters. Just takes up a little less space. All right, so there's our radius. What else do we know? Ooh, it orbits every 45 minutes. Now, you say to yourself, okay, that's a time. Well, it's the time for one trip around the planet, or one full cycle. And so that is actually the period, expressed with a capital T, of the satellite. It's 45 minutes. Again, our times need to be expressed in seconds. And 60 seconds in each minute, so 45 minutes times 60 will come up to be 2,700 seconds. So there's our period properly expressed in seconds. Let's see, and we know the mass of the satellite. So the mass of the satellite is 200 kilograms. All right, well, we're actually asked for Fc, so let's write that down. And the way that we'll calculate that, that is going to be the net force on the object. So just as F net is equal to mass times acceleration, the centripetal force is equal to mass times its centripetal acceleration, m times ac. All right, so you see that Fc is equal to 200 times, and then we realize we don't have a value for AC. All right, well, that might stop a lesser student, but not us. We'll go ahead and just calculate it as well. Now, AC is equal to the tangential velocity squared and divided by the radius. Awesome. Well, the radius is there, and the velocity is also conspicuously absent. Well, let's see if we can't find it. And the tangential velocity can be calculated from distance divided by time. The distance the satellite travels will be equal to the circumference of the circle, so that'll be 2 pi r, and then divided by the time, which is the period, and that'll be 2,700 seconds. And at this point we do in fact have all of our variables, so let's get about solving for this. 2 times pi times our radius, which is, remember to express that in meters, and so 9 times 10 to the 6th meters, and then divided by the period, which is 2,700 seconds. Don't forget to put things in proper units. If you don't do that, you're just going to end up frustrating yourself as you get things incorrect and throwing points away for no real reason. If you're going to lose points, do it for good reason, not because you forgot to convert your units. All right, So at that point, VT will be equal to, crunch the math on that, and wow, that thing is really moving, 20,944 meters per second. But I guess you got a long way to go and not much time to do it, then you better move quickly, eh? Alright, so there's our tangential velocity. Well, let's bring that over here and put that into our expression for centripetal acceleration. So 20,944, and remember that number is going to be squared. Be very careful with your order of operations so that you don't do things out of order and get an incorrect answer. And let's see, radius again, 9 times 10 to the 6th meters. And once you put those numbers in your calculator, you'll get 48.74. Again, these are rounded values, meters per second squared. All right. Well, all that needs to be done now is to place that over here in place of AC. And when you do that, 200 times 48.74, you end up with something around 9,747.8 newtons, and that's a rounded value as well. And in fact, at this point, we're talking about the force of gravity on a satellite that keeps it in orbit, and so really we would probably be better just rounding that to 9,750 newtons. Just keep the change there, and we'll go with a nice round value. Again, that's not a hard and fast rule. It just sort of works out a bit neater. If that bothers you, feel free to go ahead and write out the full 9,747.8 newtons. And of course, if you're worried about how can I know what's acceptable to round to on my test, just kind of look at the rest of the numbers and see that all your given numbers had about something in the order of just a couple of significant figures, and so that's probably most appropriate. Let's not be rounding to the nearest million or anything, though, and just rounding all of our answers to 0. That's not cool. All right. Well, I hope that was helpful, and good luck.